Hi, my name is Chad, and as I mentioned in the previous video, in this module, this episode, I'll be going over how to select a model for time series forecasting. To begin, we'll be talking about three different cases. The first is when there's no seasonality in a week trend, next when there's seasonality and trend, and then lastly, we're talking about more complex models where you have holiday spikes and changing trends. So first of all, when there's no seasonality in a week trend, you can use something called simple exponential smoothing. And this is essentially a weighted averaging technique where you place greater weight on more recent observations. For example, here, our goal is to basically predict the smoothed average at time t, and we have observations at time 0 and time t minus 1. And here we have one parameter to control. It's called the smoothing constant, which is between 0 and 1, and it controls the forecast's responsiveness. So the formula looks like this. You can see that it's actually recursive because at time t, it's actually using the smoothed average at time t minus 1. So we can expand this recursively to show the following structure underneath here. And then we can see that if we plug in different values for alpha, we can affect how responsive or how much weight is placed on recent observations. So for example, if alpha is closer to 0.5, you see that more weight is placed on the most recent observation by t minus 1 than if alpha is small, like 0.01. And to sum this up, as alpha increases, we see a larger weight placed on more recent observations, and therefore we see that the forecast is more responsive. Another approach to use when there's no seasonality and a very weak trend is something called autoregressive integrated moving average, short for REMA. The idea about a REMA is a fitted regression model that builds a model on previous observations, error terms, and differencing. It's a very complex model, so we're just going to go over a quick overview. But pretty much, we want to forecast the time series at time t. We have previous observations. We're going to apply differencing to these observations before we build our model. And then we're also going to see these constants and model coefficients appear because, again, it is a regression model at the end of the day. So our parameters are collectively called the order, and there's a P, D, and Q. And the P is the number of past observations to include. So we see that the model here is essentially a regression model where you have some coefficients, C, beta, and then we have these phi's here. These are like our coefficients. And we have other terms, which is our Y, and then our error terms. These are the data points we're feeding into the model. And the P refers to the number of past observations to include, which is essentially this part here. It's how many terms we want to include. This is the term t minus 1, the most recent observation. This is the term t minus 2, which is the observations two time periods ago. So it's looking at how many terms to include here. D refers to differencing, which is a technique to remove autocorrelation from the data set. And the idea is here you subtract consecutive values in the data set. So for example, if you have an observation at time I, you subtract the observation yi minus the observation at time I minus 1, which is the basic observation right before that. So that's the idea of differencing. It is a process to remove autocorrelation in the data set. And you would perform that on the data before building any type of REMA model. The next parameter is called Q, which is the number of error terms to include in the model. Q refers to this part here. These error terms are the difference between what we actually would have predicted in the past and what we actually observed. And we basically can calculate this error for different observations at time t, t minus 1, t minus 2, and so on. And the number of error terms to include is what we denote by Q. So this is a very quick introduction to what a REMA is, and it's a very complex model. But the idea is here it's a regression model that's built on error terms and previous observations, and it uses differencing. Next, we'll begin talking about when seasonality and trend is present. So this is typical and what you see in most data sets. Trend can be broken down into two types. There's multiplicative, where the trend is increasing over time in this kind of curve fashion, where it's increasing exponentially or in some type of growing pattern. And then you have the additive, where it's basically increasing kind of linearly with time. Seasonality has two types, multiplicative and additive again. Multiplicative means that the pattern is getting more, it's increasing more over time, it's getting more and more severe, whereas additive peaks here are just kind of constant, relatively constant with time. So the natural extension of the simple exponential smoothing model is the triple exponential smoothing model, also known as the Holt-Winters method. And the idea behind here is we can take a simple exponential smoothing model and break it down into different components, and then use simple exponential smoothing on those components of the forecast. So we are going to basically we're going to be forecasting at time t plus h in the future, and then we are going to be using these previous observations. And now we have three parameters, alpha, beta, and gamma. There are some smoothing constants between 0 and 1, which we saw are very similar to what we saw previously. But each of these controls the trend, the level of trend and seasonality, which we'll dig into shortly. And similarly, we saw that with the simple exponential smoothing, that as alpha, beta, and gamma increase, the forecast becomes more responsive. And that's exactly the thing we'll see in this model as well. So, first of all, we have the additive triple exponential smoothing model, which is basically explained here. The forecast is the sum of some level component, a trend component, and seasonality. And each of these components is calculated very similarly to simple exponential smoothing, where it's a kind of weighted average here. And explain that we would kind of use the same procedure here that we use for simple exponential smoothing to build the ST recursively, and then the GT recursively, and all these terms recursively. And then we could initialize using the initial time series data sets, y0 and y1, and so on. And then to note, this is the additive model we would use for when the trend and the seasonality is additive. There's also a multiplicative model, which is very, very similar, but it has some slight differences, but it's something you should be aware of and use when your data set has a multiplicative trend and seasonality. So we talked about ARIMA. Now we're going to talk about SRIMA, which is the seasonal extension of it. It's very similar to the ARIMA model. However, you add a few terms to account for seasonality. So it has the original terms that we explained in the ARIMA model. You have to add a few terms to account for the seasonal order. And they're essentially the same. We have a P, a D, a Q, and the M now refers to the number of periods in a year. So it would be 12 for weekly data, for monthly data, and 52 for weekly data. And the idea here is that these additional terms, P, D, and Q, allow us to account for observations from previous years. So we saw in the ARIMA model that you might use, the previous month and the month before that and the month before that. But the SRIMA model should look at, if you look at December, it's going to look at this year's December, last year's December, the December before that, and so it's going to look at the time series of just December observations. And on those December observations, we look at things like the error, and then the we perform difference over that, and it's basically looking at historical observations in the corresponding period. So now we're going to talk about some more complex models. This is made possible by an open source package called Profit, which is made by Facebook, and a lot of the work is abstracted away by an API, but I'm going to give you a quick overview of what's happening under the hood with this model. So our forecast at time t is the sum of three components, kind of like our simple exponential smoothing. It's made of a trend function, which is this kind of curve that kind of fits to the trend, and it's capturing the non-periodic changes. And that's GT here. ST is a seasonality function, which is this Fourier series that captures how the seasonal pattern changes throughout the year. And we can adjust, we'll explain later, we can adjust how exactly this Fourier series is, how much or how smooth it is using the parameters of the API. And then you can also add holiday effect. So this kind of, this really pointy function here is representing holidays, and when you have peaks at different holiday seasons, at different holiday points. And then lastly, there's an error component that is something that's not captured by these components of the model. And basically what makes this Profit basically library special is that we can control a lot of these different basic inputs very easily. So we can add custom change points. A change point would be here and here with a trend change. We can actually add custom points if we see that we would see or we expect different changes to happen in the model over time. We can also, as I mentioned earlier, change the Fourier order or the smoothness here. And then we can also add custom holidays or events. So we have, this set of typical holidays here, we can add our own as well. And there's many, many more things we can do, but these are just a handful of ones. As you can see, it adds much, much more flexibility than a lot of the previous models. And you can read all about it at the Profit docs, which you can Google, and you can click on the link in the slides to get to as well. This was just a quick overview of some typical time series forecasting methods, but there's a variety of other methods you can look into as well. Well, next module, I'll be talking about some of the Jupyter Notebook, where you can actually see some of these models here in action.